The frictions and the weight of the bar are not considered. Okay, cool. That's nice. The length of the bar is L, and we have 3 meters at one of the bar and 1 meter at the other side of the bar. What it asks is when the bar is as it is in the second figure, probably the second schema, what is the kinetic energy of the object? The object with the weight of M in mgl. Oh, 3 mass and... Okay, so this is what you have here. So you've got a pivot, and then you've got a bar, and it has length L. So this distance is L over 2, which is equidistance of this, L over 2, so that doesn't really matter. What does matter is that this is mass M, and this is mass 3M. And then in the second picture, you've got the bar. It is at an angle here of 60 degrees. There's mass M. Here's mass 3M. And what you're looking at is what is the kinetic energy of the object? The object with the weight of M. So just a clarification, do I just want the kinetic energy of this object? Okay. So how do we want to go about this? That's 30. That's 30. That's 60. And we're not worried about the weight of the bar. Okay. So that means we don't have to worry about moments of inertia or rotational features here. So what we should be, and they want this in terms of mgl. So mgl is, so if they're looking for terms of mgl, mgl is really a potential energy due to gravity. So what we can say here is that let's figure out how far this has dropped here, and then this has moved here. They actually give us a hint in this problem because they say that the sine of 30 degrees is 1/2 or 0.5. So what we can say here is that with these distances being L over 2 on the hypotenuse, we can say that on our left side of things here, using this equation, we've got 3m times g, and then the distance it fell is actually the hypotenuse, which is L over 2, multiplied by the sine of 30, because that will give us this distance right here. So this is actually going to be L over 4. And like I said, this is, in reality here, this is L over 2 sine of 30 degrees. Mathed, that gives us 3/4 mgl. Okay. At the same time, this has been raised up some distance. If we take a look at this kinetic energy of the object, its mass is m, or the potential energy it gained. That's m, g, and then sine of 30 once again of L over 2 gives us an L over 4. We are losing potential on the left side. So because we're losing potential, we're gaining kinetic energy. So this object has lost 3/4 mgl, but that means it's gained on everywhere that much kinetic energy. At the same time, it's gained this amount of potential, so it has lost that amount of kinetic energy. So what we really want here is, because the conservation of energy has to exist, and your change in energy as a whole has to equal 0, the change in the potential due to gravity has to equal the change in the kinetic energy. So the way we can kind of think about this is, we have lost 3/4 mgl potential, and we've gained mgl/4 potential. If we take a look at this, this will give us, when we add these together, -2/4 mgl, which is the same as 1/2 mgl. And this is equivalent to the change in kinetic energy. And probably what makes more sense is, really, this should be a positive value. The justification for that is that we are losing the potential, so we're gaining the kinetic. So I have a feeling that mgl/2 should be your answer. Is that an answer there? Yeah, your answer B there is 1/2, and it wants it in terms of mgl, which is what I found as well. So I would say it's answer B, assuming that we don't care about the mass of the rod itself or the pull, so, or the friction in it. So that's what I would get. And hopefully that's the right answer. Otherwise, I look foolish. Hopefully that made some sense there. But it says E. It says E, 1/8. I wonder if they want us to do... I wonder if they want us to do rotational energy. I wonder if they want us to do this. Since these objects are rotating, then oh no, you know what? Yeah, we have to split them. It's not even a rotation thing. This is the total. This is the total kinetic energy of the system. Of this 1/2, of this 1/2, 3/4 of it is going to go to the larger mass, so you're going to get 3/8 there, and of the 1/2, 1/4 of it is going to go to the smaller mass, and you're going to get 1/8. That's the total energy. I'm sorry about that. Oops, too many squiggles. Yeah, you don't need to do anything with the rotation because they ignored that. That's the total energy. I'm sorry there. Your answer is E, the 1/8. You have to split it. Yeah. Yeah, this is a total kinetic energy. It's the total kinetic energy of everything going on there. Yep, definitely got to split. If they just wanted what's the total kinetic energy of the system, then you could just say 1/2. If they wanted of the larger object, it'd be 3/8. If they want the smaller one, it's the 1/2 there, because they're both moving. B is what I would say is the quote-unquote trick answer.